Hi, welcome back. We're still talking about how EM waves propagate, and in this video we're going to talk about polarization, which is a word that you know already from our course. But when we talked about polarization previously, we were discussing materials, how materials can be polarized. Here, same word but different meaning, we're going to talk about what it means for an EM wave to be polarized as it propagates, as it moves through space. So let us check that out. Okay, so we have been analyzing EM waves with the electric field basically only in the x direction, and then from Maxwell's equations, h is in the y direction as the wave propagates in the z direction. Remember, all of those things have to be mutually orthogonal or perpendicular. The directions of E and H within the plane perpendicular to Z may change, though. They certainly don't have to be in the X or the Y direction. So a complete description of the wave, the EM wave that is, would include the instantaneous orientation of the field vectors. The polarization is the time-dependent electric field orientation at a fixed point in space. And the magnetic field orientation can be found with Maxwell's equations. So when we talk about polarization as the wave propagates, we always talk about the direction of the electric field by default. So we can have different types of polarization, and the first is linear polarization. Now, if E is fixed in a straight direction for all times and positions, we would say the wave is linearly polarized. So, for example, the waves that we were looking at when the electric field was only in the x direction, well, that's a straight line that points in the x direction. So that would be linearly polarized. So if the wave propagates, let's say, in the z direction, E, the only requirement is that E is oriented such that it's perpendicular. So let me just draw a little diagram here. Let's say the wave is coming out towards you, so the z direction is out towards you. That's the direction of propagation. Then if that's the z-axis, here's the y-axis, here's the x-axis. Anywhere in the xy plane, a vector drawn anywhere in the xy plane would be perpendicular to the direction of propagation, then the z-axis. So if the wave is propagating out towards you, the electric field may be anywhere in that xy plane. For example, like this. So it has an x and a y component. Okay, but that would be linearly polarized, even though it doesn't align to the x and y axis. So here's the y component, here's the x component. Okay, and then if we use Maxwell's equations, we can show that the magnetic field, remember, has to be perpendicular to electric field and the direction of propagation, and so the magnetic field would be like this. And so the magnetic field too would have a y component and an x component, like that. So if we know that the wave is propagating towards positive z-axis, then in general we can write the electric field as some amplitude in the x direction, which will represent as EXO, like that, or EX naught, plus some component EY naught in the y direction. And we might have some loss in energy, e to the negative alpha z, e to the negative j beta z. So this is the phasor notation. So if that's the case, then we can write equivalently h of s, or similarly I should say, h of s is got some component in the x direction plus some component in the y direction. It must be the case, again, in general, if the wave is propagating in the z direction. Okay, and then recall that the amplitudes of the waves, the electric field and the magnetic field components, they're related by the intrinsic impedance eta. So we can rewrite H as this thing here. I'm actually going to write negative EY0 like this over eta in the x direction plus EX0 over eta in the y direction times e to the negative alpha z e to the negative j beta z. So how did these components get mixed up? Why do we have a y and then an x here? Why do we have an x then a y here? And where does this negative sign come from? Well, this comes from the geometry of the cross product and the fact that E cross H has to equal the direction of propagation. So if the electric field x component is in the x direction, and if this thing is propagating in the z direction, then the x component of the magnetic field has to be, as I show here in green, negative. And then similarly, we have the y component is related to x cross y. That will give you the propagating in the z direction. So this comes again from the geometry of the cross product. So in this case, the electric field then, we can write in phasor notation like this. Times, so we've taken the real part, so the real part is the cosine of omega t minus beta z. Okay, and then it has a y component as well, so we would add, or we'd put ax here, of course, and then we would add to it ey0, or ey0, e to the negative alpha z, like this, cosine of omega t minus beta z in the y direction. So that's the electric field, right? So we're just tacking on the time dependence now. Now, if this thing is going to be, so this was for linear polarization. Now, if this thing is going to be circularly polarized, this will be the case when the amplitudes EX0 and EY0 are equal. So for circularly polarized, two things need to happen. For one, EX0, the amplitude in the x direction, has to equal the amplitude in the y direction, so we're just going to call that E0. And this is, again, assuming that the wave is traveling in the z direction. It doesn't have to travel in the z direction, but the other two directions have to have the same amplitude to be circularly polarized. And the differences in phase of these components must be an odd multiple of pi over 2 plus or minus pi over 2. So we're going to call that difference in phase delta phi, and I'm going to write this plus or minus n times, it's actually an odd multiple, so how am I going to express that? Let's say 2n plus 1 times pi over 2, where n is any integer. So think about if n is 0, then we just have pi over 2. That's an odd multiple of pi over 2. If n is 1, then we have 3 pi over 2. That's an odd multiple of pi over 2, and so on. Okay, so now to be circularly polarized, then the electric field reduces to the following. we would have that amplitude, which we're calling E0, the common amplitude, cosine of omega t minus beta z ax, and then we would have that same amplitude, E0, e to the negative alpha z cosine of omega t minus beta z, and then we would have plus or minus some odd multiple of pi over 2. And just for convenience, I'm just going to write pi over 2. I'm going to drop the whole 2n plus 1 thing and just say, okay, the phase difference is pi over 2. Although it works, what we're going to do here works for any odd multiple of pi over 2. Now, we want to see, well, what kind of wave or what kind of geometry is this thing if we were to plot it in this original coordinate system that I've drawn at the beginning of this video. So in order to do that, right, this is an electric field, and to plot the electric field it requires two plots. Actually, in this case, we have z, we have t, yeah, so two plots. So we're just going to pick a fixed point in space. And what better point to pick than, how about z equals 0? Okay, so at z equals 0, I would have the electric field at 0 comma t equals. So I plug in z equals 0, and I have E0 cosine of omega t ax plus E0 cosine omega t plus or minus pi over 2. See, so that's really nice. So you want to choose here, this should be a strategic value for z, just to get a flavor of what this thing, what's happening here, what's going on with this electric field. Now, remember that cosine, when you give it a phase shift of pi over 2, actually that's related to sine. So we can bring the common amplitude out. So this is cosine omega t, and then minus plus sine of omega t. I guess there should be an ax there and an ay here, the x direction and the y direction respectively. And we're going to write this as ex, so this is the x component in the x direction, plus the y component in the y direction. So what we're saying there when we write it like that is that ex is equal to that common amplitude E0 cosine of omega t, right? That's the x component. And we're saying that EY is minus plus the common amplitude times the sine of omega t. That's the y component. Now, here's the interesting part here. If you consider the amplitude of this thing, amplitude squared, so that would be, the amplitude is the square root of the sum of the both pieces squared, so that when you square that, the square root goes away and you're left with the sum of both pieces squared, like that. So when you do that and you apply the trig identity, sine squared plus cosine squared equals 1, then what you see is that you have this relationship between the x and the y components. And this is a constant, right? That's the common amplitude squared. So this is the equation of a circle, that as time goes by, this piece changes, but this relationship holds for all time, right? So we conclude then, that our electric field, or our EM wave, is circularly polarized. So now let's just draw that here. Again, let's say that the wave is coming out at you. So that's the z-axis. So here's y, here's x. And so what is happening here is that, that's my best circle on the fly, that at any time the electric field is somewhere on this circle. Okay, the electric field is pointing, I guess the magnitude is constant, it stays on this circle, so it's going around the circle. And this angle, well, this is omega t, right? And so, it still has a y component. Here's the y component. EY, and here's the x component. So with time, the x component and the y component changes, right? But the square root of the sum of those things squared remains constant as it goes around the circle. And remember, the wave is coming out at you. So there's actually very nice animations online about this. So you can check those out on YouTube. Circularly polarized um, EM waves. So these waves can be generated by a helically wound antenna or two sources that are oriented perpendicularly with currents that are out of phase with each other. And this is done in FM communication. So the advantage here, if you have a circularly polarized electric or EM wave, then the advantage is that reception of the wave does not depend on how you orient your antenna. So, if you're old school and you got an antenna to your TV, right? You got these bunny ears. You have to move the bunny ears around to pick up your station. But if the station is broadcasting with circularly polarized EM waves, then it does not matter how you have your bunny ears situated or oriented. Now, remember we could have a plus or a minus here as the phase difference. Now it turns out, and you can show this with some trig, but if you have a plus there, then that's called left circular polarization. So the plus is left circular polarization, and what you can do is you can take your left hand. You should do this now with me. With your left hand, which is unusual, point your thumb towards direction of travel, which is out of the page, and then your fingers curl in the direction of evolving electric field. So that would be this way, if you did that correctly. So if you're looking at this, if you could see this electric field move and you're looking at it, then you would see it going clockwise as the wave comes out at you. Now, if you chose the minus sign here, or if those were out of phase by minus, then we would call that right circular polarization, and it's exactly for the opposite reason. So if you take your right hand, you point your thumb in the direction of travel, which is out of the page, you'll see that your fingers curl this way. The electric field would move counterclockwise in that situation. So that's circular polarization. And circular polarization is a special case of elliptical polarization. When those amplitudes do not equal one another, but the phase is still an odd multiple of pi over 2, then we have elliptical polarization. So let's kind of repeat the same argument that we did for circular polarization and show that this is indeed an elliptical. The electric field carves out in an ellipse. So we'll pick a point in space that we're going to observe. What better point than z equals 0, right? And we've got an x component to the electric field. Okay, and this is what I'm going to call Ex. That's the x component. And then there is a y component as well. And we're going to say that that is plus or minus pi over 2. So we're just dropping the fact that they're odd multiples. Okay, I don't want to carry around the 2n plus 1, so I'll just let n be 0 here so that they're out of phase by pi over 2. And we'll call this thing Ey. That's the y component. So now, if I let Ex equal this thing, in other words, cosine of omega t is equal to Ex over the amplitude, like this, right? And I let Ey be this thing, and we can apply a trig identity, right? We can bring the sine in here, right? And so then we can solve for sine, and sine is minus plus Ey over E0y, like that. Now, if I square both of these equations and add them together, what I get is 1, because sine squared plus cosine squared equals 1. Then ex squared over e0x squared, which is the amplitude in the x direction, plus ey squared over e0y squared, and that is indeed the equation of an ellipse. Okay, so that gives you an idea of how the electric field can take on different geometries, right? We have linear polarization, which is it just points in a line. We have circular polarization, and we can have elliptical polarization or no polarization at all. No polarization at all. Now we're still talking about how waves propagate, electromagnetic waves propagate, and in the next video we're going to look at how much power that is the electromagnetic wave carrying as it propagates. I'll see you then. Thank you.